last people that are realizing they're in the wrong room.
Okay.
Hi, my name is Stephen Heminger. I work for Brocade, and I do a lot of kernel things and a lot of things with our data plane routing. And this talk is about the things we discovered in the DPDK and using the DPDK to build our application. So our application is not open source, but people do build applications that are open source with the DPDK, and this is our way of sharing the insights that we learned while building the application. I'll give a quick background. I'm not sure if everybody's familiar with the DPDK, and there's a follow-on talk where some more information will be. We've tried to coordinate a little bit. We'll have to see how this works out. And I'll give some examples and some things that we learned, some key performance issues, and talk a little bit about what are the issues that we've had dealing with the DPDK as well. The first fundamental thing, the whole reason this exists is our original product used Linux for network forwarding. With Linux network forwarding, you can handle, does really well as a server. You can handle about 1 million packets a second, no problem. But at 10 gig, that's what this picture's at. At 10 gig, and we want to be a router company, we need to do minimum size packets. With a minimum size packet, you have 67 nanoseconds to process it. Over here is what was with the Linux stack. You need different technologies. And the DPDK was our starting for that. The DPDK started out as a library environment that came from Intel. It's now an open source project with multiple companies contributing. We don't have the minors of the governance worked out, but that's another issue. The good part, if you've ever dealt with hardware, when you get a spec for a chip, the spec for the chip is good, but what is just as good is the tech notes. The tech notes that show you how to take this chip and turn it into an alarm clock. The tech notes that allow you to take an op amp and turn it into something to make a control system. They are the insights that the engineers, while they were developing it, used to test it. So Intel has done a whole bunch of examples. There's a layer 2 forwarder that's basically just a switch, taking packets in off one Ethernet, sending out the other one. There's a more advanced one that does routing. There's another one that does some basic firewall functions, a load balancer, and a QoS example. These aren't products, these are just examples. They're about like the alarm clock sitting on a breadboard. We started out with the basic L3 forwarder application, which just receives packets, does a route lookup, and transmits them out the other end. And this was a really useful example for several reasons. First, we could look at it, we could tune it, we could measure what was going on, and we could gain some insight on how that would work, what the timing would look like, what the overall starting point would be. So the route lookup here is one step. I measured, the last time I gave the talk of the internals of our product, about 30 steps. And that was only for IPv4. So the step from breadboard to real product is very big, but the infrastructure and environment stays the same. And the basic structure of all these applications is what sometimes referred to as run to completion or hungry puppies or whatever you want to call it. Basically read packets, do something, process packets, send them out, go back to beginning. So every application there has a set of threads that are doing some form of this worker model. Also, the other thing that we did as we got forward is we kept track of statistics internally of how many packets were processed at each stages here. And we also measured the iterations of how many packets are processed at each point, and I'll get to why that was useful later. So when you do these kinds of applications, remember I said you have 67.2 nanoseconds to process a packet? These are the breakdowns from Jesper's talk, which was at LCA. Pretty much the same data shows up multiple places. You have about 200 clock cycles at a 3 gigahertz processor. Well, you got that. That's your budget. An L3 cache miss on a current generation Intel Xeon processor is about 8 nanoseconds. An L2 cache miss is 4 nanoseconds. So you get some cache misses. You get about 7 and some change, and that's it. And what's also interesting is, notice the atomic operations. So anything that is a compare and swap or your spin lock, unlock, they count basically as a cache miss. And another one that shows up as a cache miss, and you can't do anything about it, and if I can go back here, this receiver process has to check whether there's a packet ready. That means it has to read something in hardware. That thing in hardware is not in the CPU cache. On the current generation of processors, the data will be in the cache waiting, but you have to go read the flag on the doorbell to see if there's data. Likewise, you have to go poke something over there to make something transmit. So no matter what, you've already paid you paid 2 of those taxes already. Now, this is important. I suppose if you were a real academic, you could get down to exactly how many cache misses you need to do a function, and you could design an algorithm of whatever. But we use this as a measurement as we're looking. The database world has gotten to the point where they say for a real SQL database, you need to do 3 reads and 2 writes for every transaction if you're going to do a full SQL database. We aren't there with networking, but I'm sure some academic will come up with that model. So when you start to build an application into DPDK, there's really 3 alternatives. And the first is you can say, I have a legacy application. I'm going to put a lock around it, and I'll go glue on DPDK on either side. Or maybe you've got a really good legacy application that's smart, and you don't have to worry about that. And that's really what the people have done with Open vSwitch, gluing it into the DPDK. It's really a legacy glued into DPDK. The other one you can do is you can say, I'll take the BSD code because I can't really suck GPL code in, so I'll take BSD code and I'll glue the BSD code in as a legacy. Or the last one is you can do it DIY, and you can basically build what's been done for 20 years from scratch. We ended up doing a combination of those 2. We started with BSD stuff, and I'll show you a couple examples of places where, as we were refining, we basically chopped it away. So internally, it really doesn't look like BSD. It isn't BSD, but that was the starting point because we didn't want to build everything from scratch. So, got all this stuff. How do you test it? Well, the people in the home, I actually didn't mention this. I work out of Portland, Oregon, and Brocade has offices many places, but the main office is in San Jose. The people in QA have bought really expensive Spirent things with multiple cards that can do 10 and 40 gig, and they don't really give me $1 million chassis to go test my stuff. So what I do is I use FreeBSD, which has NetMap. You could probably use the DPDK packet gen, but it wasn't available at the time, to generate packets down one fiber, run it into my router test platform or platforms because I have multiple environments, and then run up back to my Linux desktop. So I'm able to test 10 gig throughput fairly simply without creating a huge expensive test bed. And I bring this up because sometimes people feel like, oh no, I could never do this because it's really expensive. If you can find two white boxes in the box you want to use, you can test it. It almost becomes more expensive to get the network cards. So internally, what we do is we measure how many packets a second are processed. And these are the device names that show up. Those are kind of the device names that came off some other stuff that was done. But basically, it breaks down by here. I have an 8-processor system, of which 6 of them are being used for packet forwarding. And the first one is receiving 14.9 million packets a second. The other one is going out with 11.19. And that was actually a bug which was caused by that. The reason this is important is I think it's really good to put metrics in your application so you can see what's happening without having to look at either end of the system. Because as soon as you see performance issues, you want to know at which component the problem occurs. And the best way to do that is build in infrastructure that measures that. And the main tool I used for all these things was Linux Perf. Because Linux Perf lets you see by thread, by application, drill down what's going on in the application, where the hotspots are. It integrates all support for all the CPU counters. You can spend more money on more expensive tools, and you can get different data out. I don't think it's bad that Intel sells a tool and other people sell tools, but this was a simple tool, worked out of the box, it was ready to go. And if you have the source and symbols, you can draw down the line number, and you can see this line number is causing the problem. So here was the first, by the way, this is old, example. Well, gee, I was running full line rate. I was spending way too much time here. And I'm going down here, and why? I didn't have a firewall here. What's going on? Why is the firewall taking anything out of me? I looked and puzzled, and I'll get to the answer later. So the first sample applications you see in the Intel DPDK have a threading model, and you basically have to decide a threading model of your application. And the basic ones work by taking packets in, spreading them over some set of receivers, some set of cores working over it, and then who transmits. The initial ones had one receiver per core, one transmitter per core. And we used that initially, but there was a couple of issues. First of all, remember I said that you take a cache miss here and a cache miss here? You can actually do better if you split them up. Also, we had functionality we wanted to provide on the transmit side, like QoS, where you don't want to have to provide locking. If you did this model, you'd have to have some form of locking between these two about which packets you were going to send. By doing this, all that can be done here. So we use actually, this is the model that's in the QoS sample application into DPDK. Packets come in, spread over two receivers, cores processed, go into a packet ring, which is a lockless ring from the DPDK, and on out. We also did some tests with how many receiver threads you want. There's a trade-off. As you have more receiver threads, they are less likely to get packets, and they're also bothering the hardware more. So if you get to a huge number like 8 receiver threads, all those threads are chewing PCI bus bandwidth to find out about packets that aren't there. So the trade-off is how long it takes you to process this versus how many, which is gets you scaling across cores versus how many cores you have. So 2 seem to be the optimal for right now. As we went through, we discovered many speed killers, and I'll get to them in a second. Obviously, you don't want to be doing I/O operations. You don't want, if you're doing virtualization, hypercalls, system calls. This is kind of from the worst to the best. And I'll get to some of the examples of this. Also, we discovered that at various times there was different clocks being used. If you use some of the ones like the HPET, it causes an I/O operation to go read the clock time. So the first one we discovered is the examples use read TSC as the measurement for how many cycles to try to optimize how many cycles should I run before I do some work to push a packet out. Well, the trouble is the read TSC is a CPU stall cache miss because it has to get the actual cycle time. Normal Intel processors handle multiple instruction flows together. So your instructions that you appear to have written in C code and then got appear to be written in linear assembly code are turned into data flow in the processor, and they're running through multiple execution units. As soon as they see that, it's like, hold it, stop, we have to get the time, and then they keep going. So by measuring it, you actually make the problem worse. And the simple workaround we did for this was, all this was kind of thing was being done was to decide to optimize for how much bursting to do. So the answer was, don't do this, just go a fixed number of cycles. So the next one, I'm going to speed up a little here because I'm running short. The IP firewall stuff, which we started out with the BSD, had things like this, a fixed structure, which they initialize some elements. Well, the C standard says you have to zero out all the other parts of that structure before you go forward, which the compiler generates a nice string instruction to do. String instructions are a CPU stall because it does not know what the data is going to be after that point. So the answer was, don't use this, just initialize the fields that you care about, or better yet, use a reasonable argument passing mechanism so you don't have big global data that gets initialized. The next one that showed up was when we were doing QoS, we would get 5 gigabytes a second out of it. This is a 10 gig interface. What's going on? And it came down to perf put its smoking hand of destiny right there. We're doing a floating point divide for every time we ask to get a packet. I don't know about you, but it turns out floating point divides are about the slowest instruction you can ask a processor to do. I've got a patch that's about to go out that just changes that all to basic scaled math. You can do even better by turning that divide into a multiply, but that's more of an exercise left to the reader if you just get rid of the floating point. So the answer to that is don't do floating point in your packet path. The other one we discovered as we were testing is what I call the value of idle. When a CPU is idle, it affects the thermal balance of the processor. Your chips inside have a thermal budget. They will do things to keep within that thermal budget. If you run too fast, they'll clock you down. Likewise, if parts of the functions can be not in use, other parts can be boosted up. So we found back in that example I showed you with the different threads that by putting in some sleeps on the idle threads, and Intel has a more complex one where they do power management, but basically keeping the idle threads sleeping a little bit caused the other threads to get much better packet processing. As a side note related to this, some of the Intel instructions also engage more execution units. So some of the magic big Intel instructions that they like to have you use will actually hurt you more because they will slow the whole CPU down. So basically, if you go 100% polling, your 100% CPU, you get no turbo boost. But we chose 250 microseconds as the trade-off between how much latency could we tolerate in the system versus getting the gain point of getting the bursting working. And we do a simple kind of heuristic saying, have we gotten packets? Have we gotten more than one packet? And just sort of a bang-bang controller to get us in and out of that. The memory layout, you need to use smart algorithms. You can't basically use linked lists. If you use linked lists, walking a linked list, basically every step causes another cache miss. If you use array-type algorithms, the neighbors are right there in the cache, so you get the walking for free. We also experimented with inlining and prefetching, which always looks good, but a lot of times doesn't help you. The processor can follow in directions pretty fast in code, but prefetching, you've got to be there way ahead of it. There's a magic window with prefetching. You've got to have the data prefetched for when you're ready, but if you prefetch it too soon, you're just polluting things. If you prefetch it too late, you're going to get to using it before it's done anyway. Locking, we basically went away from using reader-writer locks to using a LGPL library called User Space RCU, which I don't have time to explain in this talk, but the big thing about it was lockless readers. And most importantly, they have a lockless hash table. So we could do things like the ARP table and put it in a lockless hash table and not have to lock it all in the packet forwarding path. The DPDK provides a longest prefix match like this, where you get a big table, smaller table, and compute a next hop. This is like pre-calculation in a router. You're pre-calculating what the routes are going to be. You can't do this in the kernel because this table takes you 64 meg of memory. But in user space, great. 64 meg of memory, no problem at all. The problem you had with the Intel one was the size of these parts of the algorithm were too small to be usable. Also, it was missing some memory barriers, which I didn't feel safe. And the biggest one for us was when we tried with a router, full enterprise backbone router size of table of millions of routes, a route change, there was an n-squared update in there. You don't want an n-squared update with 4 million routes changing. So we redid that using BSD red black tree. And it got to be, these are so many changes that we can't, in general, we feed everything we change in the DPDK back upstream. We couldn't feed that back upstream because it became so different from the original source. Also, they tended to have a fixed size for tables. The other thing that we discovered is the best performance you can have in a hypervisor is to use PCI pass-through. And with PCI pass-through, you're taking a hardware device and giving it to the guest. That means that you need to have protection, and the protection comes from the IOMMU on the host. Well, the guest is normally sliced up in 4K pages, which creates a huge amount of IOMMU entries. The IOMMU then thrashes away, and you see a 25% performance drop running in a guest. The fix for KVM is you tell KVM to please put this guest in contiguous huge memory, and oh, by the way, to do it really well, you have it put it in contiguous huge memory with 1 gig pages, which creates, 2 or 4 entries in the IOMMU. There's no problem at all. The downside is all this requires a bunch of manual configuration in KVM. Vert Manager and all the nice GUI tools are not able to do this right now. Eventually, this will all become a checkbox. It'll be fine. And of course, there's the next stage too. If you're stuck with a proprietary hypervisor like VMware, you have to wait for them to do the same thing. And they are doing it, but it's a wait. The DPDK itself really didn't cause us a lot of direct pain, but kind of the indirect pain. Came as a source library with source mentality from developers, not distribution mentality. What does that mean? Features were compiled in and out by configuration. As a Linux kernel maintainer, there's 2 types of people. There's the hackers that like to play with the config file, and distros that basically have to build everything that will ever be used by their customers and put it in the system. We're basically distributing a product, so we have to have everything in that anybody would ever want. And the problem is the configuration of the DPDK changes. Also, they confuse the fact that the build system and the running system will not be the same. You don't want to guarantee that the only system it will run on is the CPU you built it on. And, I mean, it's great if you're Intel and you try to say, I used all the new Haswell instructions, but it's not good for customers. They also tend to have fixed table sizes, which doesn't work very well. And they also throw a bunch of things at you which you probably didn't want to know about. Like, how many CPUs am I going to do this? I have to decide at boot up. And how many memory channels? Scratch, scratch, scratch. What's a memory channel? Scratch, scratch, scratch. What's even worse is there's really not a way to find out how many memory channels are on the system reliably through all the tools in Linux. You can even go in DMI decode and jump into the BIOS and find out about how many memory chips are in there, but they don't tell you how many channels. And lastly is they tended as hardware people to expose all the things about the device they loved, all the features they thought you would want to have. I'm sorry, I don't like to set PCI bus thresholds, which are chip specific, on my software. I want to write generic software against a network device. And so we even have tables that say, if it's this driver set these values, which to me implies a bad abstraction. So I'm just about out of time. The fundamental point of this is you can do a really fast router. Actually, we get 14 million. It depends on the actual CPU. My little home box gets 12, but that's a crappy white box. As you build this stuff, there's lots of ways you can shoot yourself in the foot, and there's only a few ways to go fast. And the few ways to go fast are basically by avoiding doing something stupid, not by magically inventing anything. So with that, the time's up flag is coming, and I think I have a little time for questions. Okay. Any questions? DPDK, the question is, what's our strategies for spinning for packets? If you're familiar with the DPDK, has the basic function of give me a packet, receive packet. And we basically have the threads are, each one has a set of resources it's working against, and the threads polls for n number of packets against a device. That's where we put the sleep in, because you don't, right now with the current architecture, there's no way to get woken up when a packet shows up. So it's either ask or ask less often. It's kind of like the kid wanting a cookie, right? If he asks you all the time, you're not going to give him a cookie. And he gets the strategy, well, if I ask about once an hour, I might get a cookie. So that's what we're trying to do. Yeah. Thank you very much.